Chegg. Oh, there we go. Well, welcome, ladies and gentlemen, to Chegg Virtual Office Hours. I am your host, Brian McLogan, and I am excited to share this hour with you, helping you with your questions. You can think about this as like a virtual office hours where I'm here to answer your questions. So if you have some questions, put them down into the chat, and I will do my best to be able to help you out as you're working through pre-calculus as well as trigonometry. If this is not your first live stream with Chegg, well then welcome back. I am glad for you to join us. And if this is your first live stream, then congratulations. We are here together for an hour, and I'm going to go ahead and work through some problems that I know that a lot of students will sometimes get frustrated on, and they will kind of want to avoid making some mistakes. So that's why I curated some problems to go ahead and work through. But I also want to hear from you guys. Let me know where your pain points are coming from as you guys are preparing. We're in that second half of the season now, getting ready for exam time, and things can get kind of stressful and a lot of anxiety and some stuff that we're going through. We're still kind of worrying about everything from the first quarter, and then we got to come preparing for our test. So that's why I want to be here, and that's why I partnered with Chegg to be able to offer these virtual office hours for you guys. Just a little bit about me. I was a classroom teacher for 14 years down in Jacksonville, Florida, and I taught pre-calculus for many of those years. And back in 2010, I started recording myself and putting up a lot of tutorials on YouTube. And that is what I currently now do, is a full-time working through math problems every single day. So if you think you have it bad doing math, just preparing for the class, just imagine me sitting here in this office just doing math problems. But I enjoy it, and I really enjoy hearing from you guys. So let me know what questions you guys have as we're going to kind of work through these problems. And what I selected for the first couple problems to kind of go through is going to be our verifying trigonometric identities. And so I'll kind of work through these a little bit as kind of step by step, and to kind of explain just like if we were in the classroom. And if you have any questions on anything I'm going in particular, or a question that you are currently going on in your own class, then put it down in the chat and let me know, and I'll be happy to be able to answer your questions from on there. So the first question, we have cosine of theta times tangent of theta plus cotangent of theta is going to equal a cosecant of x. Now, one thing I always tell my students is when we're looking into verifying trigonometric identities, one of the easiest things to do is like always pick the side that's the more difficult side. And hopefully you can recognize that this might not seem like more difficult, but there's a lot more that's going on this left-hand side. And sometimes if you're not sure which is going to be the most complicated side, look for the one where you can apply an operation, right? And we want to look into, well, I want this to look like that. And if I can make this look like that, then I have verified the identity. So one thing I recognize is I have this cosine outside of the parentheses. Well, I can apply my distributive property there, right? I can go ahead and take this cosine of theta. Let me actually get this going on. And I can go ahead and multiply this to both terms inside the parentheses. And when I do that, I'm now going to obtain an expression that looks like this. It's going to have a cosine of theta times a tangent of theta plus a cosine of theta times a cotangent of theta. All right, and I'm not going to rewrite everything on the right-hand side because we know that's just equal to cosecant of x. But now what we need to do is like, well, all right, well, what can we do here? Like, there's really nothing else. I can't multiply. Like, how do I multiply by trig functions? So one thing we always want to look into is applying what we call our division property. Because if you have the same expression, term, or function in the numerator as well as in the denominator, then we can, and they're separated by multiplication, we can go ahead and divide those terms out. Well, right now we don't have that case. However, if we use the quotient identity, which is to rewrite tangent and cotangent in terms of sines and cosines, we can get something that's going to look like that. So if I have a cosine of theta times tangent, I can rewrite as a sine of theta over a cosine of theta plus a cosine of theta times cotangent, which again be a cosine of theta over sine of theta. Cotangent, cosine over sine of theta. Did I multiply? Yeah, times sine of theta. Now, what we look at is we can see we have some things that are going on, which we can see some things are going to be divided out, which again, did I already rewrite this point in from there? The voice is on the thing. I'm already looking at my first problem and I'm looking at, that was supposed to be able to multiply cosine over sine, and that's going to give me, well, I guess I'll keep on working through this, but I was like, wait a second here. That's not what I remember I had. Oh, I guess it was what I had, yeah. So now these terms are going to divide out, and that's going to leave me with a sine of theta plus, in this case, we'll have a cosine squared of theta all over sine of theta. So now, what do we need to be looking at? Well, somehow I need to combine these, right? Because you can see on this right-hand side, I need to be able to get this down to a cosecant of x. And unfortunately, I can't get this down to like a cosecant of x unless I can combine these. And I can't combine them unless they have the same denominator. So what we need to do is understand that sine of theta can also be rewritten as a 1. And so remember, when you're trying to add fractions and they don't have common denominators, what you're going to want to do is be able to get that common denominator. So in this case, what I can do is multiply by a sine of theta over a sine of theta. As long as you multiply the same expression in the numerator and denominator, that's going to be creating that perfect square, that's going to create, sorry, that equivalent fraction. And so now what I'll have is going to be a sine squared. That was a really bad squared. Sorry about that. It's going to be a sine squared of theta all over a sine of theta plus a cosine squared of theta all over a sine of theta. And again, we're trying to make this equal to a cosecant of what did I do? X. It's supposed to be a theta. Sorry about that. All right, so we can combine these. Well, now they have both denominator sine of theta. So now my numerators can combine. And one thing that you need to know that I would say, like, if there's anything, I remember when I even first started teaching precalculus, it had been years since I had taken precalculus, but I remember this identity. So please make sure you remember this identity. This identity is that sine squared of theta plus cosine squared of theta is equal to 1. So when I go ahead and combine these, I'm going to get a sine squared of theta plus a cosine squared of theta, and that is all over a sine of theta. Well, sine squared of theta plus cosine squared of theta is equal to 1 via this Pythagorean identity. So then I'm left with 1 over a sine of theta, and that is now equal to, hopefully you recognize via the reciprocal property, that's equal to a cosecant of theta, which, ladies and gentlemen, is exactly what we were looking for over here on that. So that is, now we have verified that identity. All right, the next one. So this one we have 1 plus cosecant of x divided by a secant of x minus a cotangent of x is equal to a cosine of x. Now, I think, again, we can probably all agree, what's the more difficult side? Well, that's definitely the left-hand side, right? I have a fraction minus cotangent, and it's like, oh man, this is not looking good. It just looks confusing. So one thing that I recommend to students is, even if you're not sure what to do or where to go, one of the best things you can always do is rewrite things in terms of sines and cosines. If you rewrite every function in terms of sines and cosines, sometimes that will just give you a light bulb moment of like what you can do. And it might be the correct way, it might not, but that's okay. That's part of verifying trigonometric identities, is practicing. Because I can tell you, no matter how many verifying identity problems I've done, I'll still get stuck, right? And I'll still learn new methods and techniques to ways how to approach them. But the more that I've done, the easier it has become for me. Where I remember when I was in high school and even in college, like I would struggle with them. I would take like half an hour trying to figure it out. And unfortunately, I didn't have Chegg. I didn't have online or YouTube to be able to go on and get the answers and get help. So you guys are very, very lucky. So let's go ahead and rewrite this in terms of sines and cosines and go and take a look at it. So if I go ahead and do that, I'll get a 1 plus a 1 over a sine of x divided by a 1 over a cosine of x. And that's going to be minus cotangent. Cotangent is going to be cosine of x over sine of x. Sorry, I was having a brain fart. Cosine of x over a sine of x. Okay, and we want that to equal a cosine of x. So one thing I look at this, and I'm going to say, all right, obviously, I got to get rid of this cosine in the denominator, right? And so what I can do is just like I did in the previous problem over here, if I multiply by cosine, then the cosine in the numerator and denominator are going to divide up, right? So in this case, what I'm going to do is multiply by cosine of x in this denominator. Really, you can think about that like a cosine of x over 1 in the denominator, and then multiply it over here, cosine of x. Now again, make sure you insert parentheses. That's critically important. I cannot tell you how many times students will do this. They'll forget to put parentheses here, and then they'll just have a cosine of x plus 1 over sine of x. And then they're going to spend another 30 minutes trying to figure out the problem. We don't want those things to be going on, right? So this goes to 1. That's good. That's going to divide to 1. And then up top here, we have to multiply via distributive property. So when we do that, we're going to have, let's go back to blue. So when we do that, we're going to have a cosine of x plus, now here, this again, think of this as a cosine of x over 1. So this is going to give you a cosine of x over a sine of x minus a cosine of x over a sine of x. And then what we're looking at in this case is cosine of x, well, obviously these just subtract out, right? Those are just going to subtract out. So therefore I'm left with a cosine of x. And you can see that's exactly what we were looking for up in front. So we are good to go on that case. Let me just check. Hold on one second. Let me get that moved over for on there. All right. I got a lot of these verified identities because I can tell you, ladies and gentlemen, as somebody that has gone through, prepared for a test, and one question that students will get to me is like, how can I prepare for those tests? And one thing I say is like practice, 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 practice. And especially with verifying identities, how are you going to get better at these unless you are practicing going over them? Because every single problem is going to be a little bit different, but you're going to start seeing some generalities, some patterns on a way to approach them. And that's what's going to be really, really important, that you take that practice and you can kind of come together and get some ideas of how you can approach them to problems that are similar to that. So I have, in this one, I have a cosecant of theta plus cotangent theta equals sine of theta plus divided by 1 minus cosine of theta. Now, this one, we can have a conversation. We can have an argument here as far as what's going to be the more complicated side. Are we working with the left-hand side? Or are we looking on the right-hand side? Now, if you have an opinion, what would you choose to work on? Would you work on the left-hand side? Would you try to combine those to create them into a fraction? Or would you work on the right-hand side? Because you can. A lot of students get so used to always working on the left-hand side that they just stick there. But sometimes changing it up, working on the right-hand side, guys, is perfectly fine. You just, whatever side you want to work on, you just want to remain exactly in from on there, okay? So we have sine of theta divided by 1 minus, cosine of theta. And in this case, what we're going to look at is I'm actually going to work on the right-hand side. So in this case, I have sine of theta divided by 1 minus cosine of theta. One thing that I think is important for you guys to remember, if you remember that trigonometric identity that I showed you earlier, that one is sine squared of theta plus cosine squared of theta is equal to 1, right? So if we can, when we rationalize the denominator or even this expression, what we do is we end up creating that, all right? And that's what we want to be able to be looking for on here. So I see some of your guys' questions coming in. This is awesome. If you have a math question or you have a topic that you want me to talk on, please go ahead and put it down in the chat. I think I have one more identity I'm going to go over, And then I'm going to take these questions from you guys that you guys are putting in. So if you have questions that are coming in, let me know we're on there, and then I will get right into explaining whatever concepts you guys have going in from the chat. All right, so let's go and knock out this one, and then we'll get into some of those questions you guys have. So I have cosecant of theta plus cotangent of theta. I'm going to work on the right-hand side. I don't like this fraction, and I know an easy way that I can do to get rid of this fraction, or not so much get rid of the fraction, but get rid of the 1 minus cosine of theta, is I can multiply by the conjugate 1 plus a cosine of theta times a 1 plus a cosine of theta. All right, so we're going to work on the right-hand side. Now, what's important about this is hopefully you guys recognize this creates a difference of two squares. So this now creates a 1 minus a cosine square. Oh, what am I doing here? So in the numerator, that's just going to be the same. That's going to be a sine of theta times a 1 plus a cosine of theta. And in the denominator, that's going to leave me with the difference of two squares. Like a minus b times a plus b, right, is a squared minus b squared. So therefore, this is going to be a 1 minus a cosine squared of theta. Now, I told you about the identity sine squared of theta plus cosine squared of theta equals 1. How does this relate to it? Well, watch this. If all I simply do is if I just subtract a cosine squared of theta on both sides, then I'm going to get a sine squared of theta equals a 1 minus a cosine squared of theta. So what that tells me is 1 minus cosine squared of theta is equivalent to 1 minus cosine squared of theta is equivalent to a sine squared. So now let's go ahead and rewrite this one more time. So now I have a sine of theta times a 1 plus cosine of theta divided by a sine squared of theta. Now, it's important to remember, when I write sine squared of theta, what that means is sine of theta times a sine of theta. So I actually have two sines that are multiplied by each other down there. So what I can do, though, is since everything is separated by multiplication in the numerator, and down here, that's the sine of theta times sine of theta, I can divide out one of those signs in that case. So now I'm left with one sine in the denominator, which is going to be a 1 plus a cosine of theta divided by a sine of theta. And then I can take this sine of theta and I can rewrite this as a fraction for 1 over a sine of theta plus a cosine of theta over a sine of theta. Now, when looking at it, 1 over sine of theta, using the reciprocal identity, that's going to be a cosecant of theta, which is what we had right there. And then over here, I have a cosine of theta over sine of theta, which is the cotangent of cotangent of theta, which is what we have right over there. So then we are good. All right, ladies and gentlemen, before I get to this last question, please let me know where you are coming in, because I know some of you guys are coming in from on Chegg, on YouTube, either Twitch, TikTok, Instagram, where it may be the case that you are actually located. Because I'm very happy to be on, partnering up this with Chegg and being able to be there for you guys to support you throughout this office hours. So let me know in the chat where everybody is tuning in from, whatever platform you are coming in from. I'm very interested to kind of see where everybody is tuning in from and where you guys have utilized and gotten help from accessing Trig's materials. And let's go and see what questions we got. What are my things? All right, can we cover inverse trig functions? Yes, I can cover some inverse trig functions. How do you graph the cosine function? How do you graph the sine function? Oh man. All right, well, we can go and do that. And TikTok, very well. But where in the world? Where in the United States? Where all over the world are you guys tuning in from? I am located in Jacksonville, Florida. I am wearing a sweatshirt because I grew up in Michigan and moved down to Florida and have gotten very, very cold-blooded since then. And now whenever it's cold, even though it was like nice today, whenever it gets cold, I am now like freezing around. So I don't have the skin that I used to from before. So let me see. All right, so let's talk about inverse functions. I got a lot of problems for you guys. You guys are, that's fortunate. But we'll hold off those. Now that you guys got some questions going in from there, Um, let's go out. Don't need that anymore. So let's talk about inverse functions. And I'll talk about graphing sine and cosine. All right, and let's see if anybody else. Complex numbers will, based in the UK, awesome, love it. How do you model from a given, seasonal model for a given graph? So I'll cover those inverse functions. For inverse graph, I think the main thing that I'd recommend for the sinusoidal graph is making sure you have that max and the min, that amplitude, and as well as looking in for those points to be able to identify what the period is going to be. Because if you can identify the period, you can identify the max and the min, that means you can tell what the amplitude is. And then it just kind of comes into identifying what other shifts you have, either a vertical shift or if you have a horizontal shift, and so on and so forth. Those can get kind of messy though, for me to be able to do this without like specific points in graph paper. So it might be a little tough for me to handle that on the live stream from on there. Next on complex numbers, let me know a little bit more what you'd like for complex numbers. Georgia, you're not too far away from me. Can I go over finding the pi values with the sine, cosine, tangent? What do you mean finding the pi values? Can you let me know what you mean for as far as finding the sine values on, or those values on sine, cosine, tangent? Let me know. I'm interested here, TR. All right, so this last one is not going to take too long, so I really want to go over it because it kind of goes along with everything else teaching. So let me go and knock this in, and then I'll get to those questions you guys submitted. And then also, if you're just joining to the stream, welcome. My name is Brian McLogan, and I am partnering with Chegg as far as providing you guys with a virtual office hours to help you guys with pre-calculus and trigonometry. So if you have any pre-calculus or trig questions, then go ahead and post them in the chat. All right, so this question, a lot of students will see this and they say, oh, well, let me go and rationalize the denominator, right? Kind of seems like difficult in that regard. But watch, ladies and gentlemen, sometimes you don't always have to do things the exact same way. You could rationalize the denominator, that's not wrong. But I could also just rewrite this as 1 over cosine of theta plus a sine of theta over a cosine of theta, right? Now 1 over cosine of theta equals a secant of theta. Sine over cosine equals a tangent of theta. And wham, bam, thank you, ma'am, ladies and gentlemen, we're done, verified. All right, so let's get into the question you guys asked. So therefore, I can get something in that's timely for you guys. Now, I don't know what your question is referring to on inverse functions. So I'm going to kind of go over some common missteps that students will make when they are looking into either evaluating with the inverse function or doing like some composition of inverse functions. Before I actually get to that, sorry, I'm going to jump to this question, graphing sine and cosine, because obviously we teach graphing sine and cosine typically before we get to an inverse. And I want to use the graphs of sine and cosine to be able to talk about the inverse. I think it's really, really important. So as a educational value, I'm going to do this one first. All right. And again, keep the questions coming, guys. I can see you guys in on the chat coming up there. So I will start going through these as quickly as I can to help you guys out. All right. So graphing sine and cosine. So if you know the unit circle, which hopefully you guys all should know at this stage, if you are taking pre-calculus or trig, which I'm assuming you are, we know these points, right? This is going to be 1, 0. This point is 0, 1, negative 1, 0, and then this one 0, negative 1. Okay. Now I'm only going to focus on these points. I'm not going to focus on all the little angles from on there, because what I want you to kind of think about is we need to know these angles, right? If you think about these angles, that's 0, that would be pi halves. Halfway around the circle is pi. This one is going to be 3 pi halves. And all the way around the circle is going to be 2 pi. Well, that is going to be a period of our sine and cosine, right? All the way around the circle, it just starts repeating itself. So if we're to look into graphing sine and cosine, let's just do sine of theta first. Y equals a sine of theta, okay? So this is going to be our theta axis. It's basically going to represent the angles. Now, sometimes we use x, but again, it's important to understand that represents the input, which is going to be the angle. And then our y-axis is going to be representing, actually, you know what, let's not use y. I don't want to confuse anybody that may be introductory. I'm going to use f of theta. And so I'm going to call this the f of theta axis because that's going to be the output. Now, a lot of times, again, you can use y, but let's just use f of theta because that represents the output. Now, when we're looking into the unit circle, what do we use as the output for those values? And if you're thinking about a point that's on the unit circle, if I say the sine of that angle, well, that represents the y coordinate, which is on the unit circle, right? Because every coordinate on the unit circle has an xy axis, because this is the, or xy coordinate, because this is the xy axis. So when I say the sine of an angle, y represents what that coordinate is. So let's start at 0 degrees, which is right here. What is the y coordinate? It's at 0. So that's going to be my first point. The next angle, which would be at pi halves, the sine of pi halves, again, is the y coordinate for the coordinate point on the unit circle, which in this case is going to be a1. Then I go to pi, and you can see the y coordinate is back to 0. Then I go to 3 pi halves. The y coordinate is down to -1. And then I go all the way back over to 2 pi, and you can see the y coordinate is going to be 0. So now you can see we got this beautiful shape of what the sine curve is going to look like. And when we think about this in terms of the cosine, remember cosine of theta just is the exact same thing, but now it's going to be for the x coordinate. So we look at this and we'll do the exact same thing. But now we're going to look at, I'm not going to repost those, rewrite those in, but now when I look at the x coordinate for 0 degrees, I'm at 1. Then when I go to pi halves, I'm at 0. 3 pi halves, I'm at -1. Pi, I'm at -1. At 3 pi halves, I'm back to 0. And at 2 pi, I'm at 1 again. So you can see that graph is going to look something like that, right? So that is going to be what we call the parent graph of sine as well as cosine. Now, you might be asking as far as like, well, what about when you have transformations and everything like that? I'll do a quick little review on those just so you have, but I think it's really important to know what these graphs look like, how to quickly go ahead and create them. Because as far as the transformations go, when you're looking into the transformations of a graph, let's just do a quick little review for you. So y equals a times a sine of b x minus c plus d, okay? So a, remember, is going to be your stretch and compression, but a also represents the amplitude, which is the half distance from the max to the min. So we say the absolute value of a, that's equal to the amplitude. B is going to be your your horizontal stretch or compression, but for trigonometric or sine graphs, that's actually going to be what we call the effect of the period, because if we're stretching or compressing the graph, that's going to change how long it takes the graph to repeat itself. Here, for the parent graph, we have a period of pi, right? That's how long it takes the graph to repeat itself. But when we take 2 pi divided by b, that's going to now give us our new period. Okay, and again, this can be for sine or cosine, doesn't really matter. And then the other thing left else we have is going to be d, which would be our vertical shift, up and down. So I'm just going to say that's a vertical shift. And then if we have a coefficient, bx minus c is going to be what we call your horizontal shift left and right. So that is going to be your horizontal shift or starting point from on there. So hopefully that kind of gives you a good little foundation for what you have in here. Now, if you are enjoying this little stream, I'm going to get to some of your questions. So if you guys have added in those questions, I'm going to get to some of those. But if you're enjoying this, then drop me down a little bit emoji. Let me know what would best represent maybe how you are feeling right now in your class, or maybe right now for on the stream. And drop down something. Let me know a little bit how you are feeling, so therefore I can get a little bit feedback from your chat. But I'm going to get to the inverse trig functions next. But before I get to that, let's go and see what other questions. Let's see. Do you add like there's two possible pi values based on the family? Like there's two possible pi values based on the family. Well, awesome, Neil. Good to have you. Good to have you on. Thank you for that. There are two possible pi values. Well, maybe you're talking about with the trig functions, I'm assuming. Can you go over finding the pi values with the sine, cosine, tangent? Oh, finding the yeah. Okay. I think I'll get into maybe answering your question when I get into inverse trig. So if you have that. New Jersey, can you go over find the pi values? Okay, cool. So let's all right. So now we have these. Now, what I want you guys to understand before we get into inverse functions, these are functions, right? These pass the vertical line test, right? If you were to take a vertical line, you can see that no matter where I move this vertical line, it passes the vertical line test. Right? Cool. Pass the vertical line test. Okay. So now let's go into inverse functions. So this is what the student was asking me. Can you go over inverse functions? Well, I don't know what you mean. Just want you to talk about inverse functions. So I'm going to kind of go through the basics of everything on it, and then hopefully give you a good idea of, and then do some examples for you so you can see exactly how it makes sense. Now, quick review. If you remember at the beginning of the course, hopefully you went through something that was like, I don't know, find the inverse of, a like y equals, I don't know, 3x minus 2, something like that. And we can do it algebraically, but we're not going to focus on the algebraic method. What I want to focus on is the geometric method. So if you looked at 3x minus 2, let's pretend it looks something like this. Now, hopefully you remember to find the inverse of a graph, what we simply need to do is find the y equals x line. And then what we do is we would reflect the graph about that y equals x line. And if you were to do that, you'd probably have something that looks like that, okay? So we'd call this the inverse graph. So if y equals 3x minus 2 is your function, the inverse would be a reflection about the line y equals x, okay? And again, notice how both y and y inverse are functions, so that's good. Now let's get to our trigonometric graphs, because that is where we have some issues, particularly with sine and cosine. Because when I go ahead and graph sine, it looks something like this, right? And when I graph cosine, it looks something like this. Oh, I gotta go back up. There you go. Got to make sure I do the whole period. So why don't we just do this correctly? So there you go. Now they kind of look similar to that. The problem is, and I apologize, I'd have to go and look at exactly what the graph, it is confusing to go ahead and rewrite these in that graph, but I want you to understand, and again, this is going to be wrong, okay? So, because it's difficult to go and graph it. But if I was to go ahead and find the inverse, oh, it's also important to recognize that these graphs go left and right? So they continue in both positive and negative directions, okay? So if this graph, if I'm going to reflect this about the y equals x line, I am now going to get a graph. And again, this is wrong, but go with the understanding. It's going to look something like that. And this one's going to look something like that. Now, what's the problem with that? Well, remember that vertical line test I was talking about? Do you guys see how this fails the vertical line test horribly? For at almost every single point, except for these like vertices, every single point, this graph is going to fail the vertical line test. So that's why we have restrictions on our graph. And another way to think about that is, let's go and look at the unit circle. And this is what the student was asking as far as, this is what that student was asking about, like when you get different pi values. So let's go and look at, I don't know, if I said cosine inverse of negative square root of 2 over 2. Okay, what's the answer? Go ahead and get your calculator out. Plug that into your calculator. Now, you know your calculator represents a function, right? You plug something in, you're going to get one thing out, only one answer, right? It'd be really weird if your calculator is like, oh, here's two answers. No, that defies what our answer, like a function. A function, you get an input and you get one exact unique output. You don't get input and then two outputs, right? That's not a function. So your calculator works as a function. You plug something in, you get one thing out. So if I have cosine inverse of negative square root of 2 over 2, I need one answer. But if we think about what is the definition of a cosine inverse, what are we doing? There's actually two answers we can choose from. Because if you think about this, let's look at the cosine inverse is basically, if I say the cosine of an angle, remember, equal the x coordinate, right? We talked about that in the previous one, talking about graphing. So the cosine of an angle equals the x coordinate on the point on the unit circle. So when I'm doing the cosine inverse, that's basically like the cosine inverse is that value on the unit circle, and then we want to be able to find the angle, right? So this represents the x coordinate on the unit circle, and this represents the angle that is going to create that. Well, let's go back and look at the unit circle. When is cosine, when is the x coordinate equal to negative square root of 2? Well, unfortunately, that's at 2 points, not 1. Negative square root of 2 over 2, and this point is square root of 2 over 2. So we have that angle. And then also we have this angle down here, which is a direct reflection about the x-axis. So this angle is a negative square root of 2 over 2, comma, square root of 2 over 2. So we have two angles. Well, which one did your calculator decide? Does anybody know? Put it down in the chat. Which one's the correct answer? Is it this angle or is it that angle? Which one? Let me know. Reflect y equals x. Let me see. You are switching x and y, so it's only right to reflect about the y equals x line. Yes, that is correct. As far as, I didn't talk about the swapping of the x and y's when you think about the algebraic approach. But yeah, that is exactly what we are when we look into reflect about that y equals x line. So the correct answer is this angle right here. Now, to get that answer, we could break up. We know that halfway around a circle is pi. And if we think about this in terms of fourths, right? So we know pi, so we could say 1/4, 2/4, 3/4, 4/4. So that angle is going to be a 3 pi over 4. Now, why is that the case? Well, again, remember your calculator is programmed. It has to only give you one answer. It can't give you two answers. So what we do is we have some programming restrictions on the inverse of our trig functions. So the cosine is going to be restricted here between pi. Our angles are going to be restricted to going to be, let me rewrite it this way. Cosine is going to restrict between 0 is less than our angle theta, but it has to be less than pi. Whereas we also have a restriction on sine and tangent. Those are going to be restricted between a negative pi halves, which is less than theta, which is going to less than a pi halves. Now, what I want to show you real quickly is like, what would that look like if we restricted our graph between 0 and pi? So again, remember, if you take a look at this, between 0 and pi, let's see, do I have any more colors left over? Not really. I guess I could use my gray black. So if I restrict this between 0 and pi, it's going to look like that. But what happens is now when I reflect this about the y-axis, what I want you guys to see is that would still pass the vertical line test. Same thing over here. When I take this graph and I reflect from here, negative pi halves, up to pi halves, if I reflect this about the y-axis, about the y equals x line, it's still going to pass the vertical line test. So we're going to be good. Okay, so that's why we add those restrictions. Now you might say, well, why are we adding that? Why couldn't we add, restriction of negative pi halves to pi? Like there is other restrictions we could utilize. These two restrictions gives us the largest, I would say, domain unrestricted domain that is closest to 0 that we can use. So, and that would be positive. So that's why it would be preferred. Like, yeah, we could use a domain of negative pi halves to 0, right? But we'd rather use positive values in that case, and we still want to have something close to 0. So, and again, from here, you could use like pi halves to 3 pi halves, but then it's not as close to 0, right? So we always want to be able to you work on values that are going to be close to 0, because again, that also helps you with utilizing and working with points or values that are on the unit circle, right? So a question came in from Precalc, is Precalc the same as advanced functions? So I actually tutored a couple kids that were in advanced functions. I looked at majority of the material, and it was very, very similar. As far as my understanding, advanced functions is in the Canadian education system. And correct me if I'm wrong if you're from a different country, but that's where I've heard the most about advanced functions is from students that were in Canada. So I've seen a lot of carryover, a lot of similarities. But the funny thing about precalculus and trig, every textbook that I've had has always been a little bit different. When I took precalculus in high school, we did matrices. I never taught I taught precalculus for 10 years, never had to teach trig. I took precalculus in college. We didn't do anything with matrices. So, and even though it was in the textbook, it just wasn't part of like the curriculum in that case. So, that's everything's going to be a little bit different as far as who, the curriculum guides and what they want to teach and what they're preparing you for. So I would say the general idea of the courses would be the same, and a lot of the content is going to be carryovers, but there's always going to be variations from on there. Yes, I can go over exact points of 0, 45, and 90. I actually just made a video on this going over. So I'm not going to bore you with the basic stuff right there, but let's kind of talk about maybe the unit circle. And actually, we can even go over, I'll even one up you on that. I'll go over even finding some values that are not in the first quadrant that you should know and be able to do it fast, all right? So when talking about graphing trig functions, I showed you guys these points. And I don't care if you're in Algebra 1 on the stream, you should know these points. Well, I guess you should also know how to draw a circle. So let's try that again. It used to be able to, if I held it, it would draw a circle for me. There we go. All right, so not bad. I'll take it. Let's see if I can maybe move it. All right, so let's pretend that's my unit circle, right? Now we know these points are 1, 0. This point is 0, 1. This point is -1, 0. And this point is going to be 0, -1. Right? Now, through our understanding of special right triangles, if I did a 30-degree angle here, right, and you can think about drawing like a nice little line down there, we can actually understand what the relationship or what the distance, this horizontal and vertical distance, you can think about that like a nice little right triangle right there. So by understanding of our understanding of right triangles, if this is going to be 30 degrees, or in terms of radians, which would be pi over 6, I can rewrite this, or I can identify this coordinate point as square root of 3 over 2, 1/2. Then, if I was to create a 45-45-degree triangle inside of the unit circle, again, we know that the horizontal and vertical distance from there would represent our coordinate point, which in this case is going to be a square root of 2 over 2, comma, a square root of 2 over 2. And then last but not least, if we had this point right here, so that's 30, 45, this is going to represent 60 degrees, which this point would be a 1/2, comma, a square root of 3 over 2. Okay, so if you know those points, and this is what I tell my students, you need to know those. Like, I don't want you memorizing the unit circle. I do want you to know what these points are. And let me draw it maybe a little bit bigger. You need to know those angles. So we have this one, which is, again, I prefer radians. I'm not a big degree kind of guy. I'm a radian kind of guy. So I know a lot of students get used to understanding degrees. And they're like, I just want to use degrees. Make sure you're comfortable with radians, okay? So that's going to be a pi over 4. So that's that point, and then we have this point over here. So make sure, ladies and gentlemen, this is going to be pi over 3. Make sure you know these points, okay? Please, please make sure you know these points. Because if you know these points, it's just going to make your life so much easier. That's square root of 2 over 2. Okay. So, and then this one, square root of 3 over 2, comma 1 half. And there's a lot of videos on how to create them. I'm not going to spend time on this live stream creating these points. You need to know this first quadrant, okay? You need to know this first quadrant. And then, furthermore, you need to know the definitions. Now, we talked about it for graphing, but remember, the sine of theta equals y, cosine of theta equals x, and tangent of theta equals y over x. And again, these represent the coordinate points on the unit circle, okay? So make sure that we're thinking or talking about points that are going to be on the unit circle. So if I want to do, let's say, what is the sine of pi over 4? Then you just go, all right, well, here's pi over 4. Sine represents the y coordinate. Well, that's going to be square root of 2 over 2. And I say, well, what about the tangent of pi over 3? And you say, all right, tangent is y over x. I go to pi over 3. My y coordinate is square root of 3 over 2. My x coordinate is 1 half. And now to simplify this, I could, just kind of like we did for our trigonometric identities, I can multiply by 2 over 2. And that's now going to leave me with a square root of 3 over a 1. So my final answer would just be a square root of 3. Now, I did promise you a little bit of bonus, okay? So make sure you know those. And again, you can also do them with degrees. I'm just not a big fan of them. But, notice if I said, not tangent, let's do cosine. What if I did, what's the cosine of 30 degrees? So just remember, I'll do them over here. So this would be 30 degrees. That's 45. Come on, Miss McLogan. That's 45. And then this is 60 degrees. And then that's 90 degrees. So if I say, what's the cosine of 30 degrees? Remember, that's the same thing as pi over 6. And again, we're looking for the x coordinate, which is, in this case, going to be a square root of 3 over 2. And voila, you're done. Now, real quick, what's important about the unit circle, or not so much what's important about it, what's so helpful about it, is if you know that first quadrant and you understand reference angles, you're good to go. So the reason why I bring that up is, what if I said, what is the tangent, not the tangent, let's do sine. What if I said, what is the sine of 7 pi over 6? Now, you need to understand how to graph 7 pi over 6. Hopefully you remember that halfway around a circle is going to be pi, right? And you could think about pi, if you broke that up into 6 equal parts, right? 1, 2, 3, 4, 5, 6. So each of these represents a pi over 6. So technically this is pi. You could also think about it as 6 pi over 6. So if I have 7 pi over 6, and remember when we're graphing trigonometric angles, we're starting from here and we're rotating this way, well, I'm going to go an extra pi over 6 over, which is going to be right here. Now, again, if you're one of those students that's like, all right, Miss McLogan, I memorized the first quadrant, I got it, but I'm still kind of confused on how to do pi over 6 or 7 pi over 6, you need to understand the reference angle. So the reference angle tells us is that is going to be the acute angle between your terminal side and the x-axis. That is my reference angle right there. Now, what is that reference angle? How far is that angle from the x-axis? And the answer is going to be pi over 6, right? So we can say theta prime is equal to a pi over 6. Why does that matter? The reason why that matters, ladies and gentlemen, is because the coordinate points for right here are going to be the exact same. So if theta prime is my pi over 6, I just need to go back over to, let's say, what is my angle at pi over 6? We know those coordinate points is going to be square root of 3 over 2, comma 1 half. The only difference between this angle or this coordinate point and this coordinate point is a reflection. So you use the exact same coordinate points as your reference angle, but then you just need to adjust the plus and minuses based on the quadrant that it's in. So in this case, you can see it's in the third quadrant. So my x as well as my y both are going to be negative. So therefore, this coordinate point is actually -3/2, comma -1/2. And then when I ask what is the sign, you know that's the y coordinate, which is equal to a -1/2. Whew. All right. I'm going to go and take a look at your questions. But one thing that actually always interests me is what are you guys coming to virtual office hours for? Like, what do you want to, what are you going through? What is your major? What are you looking into going to school for? What is it you're trying to achieve? Are you just trying to improve upon your grade? You know, like why have you hopped on a live stream? Why have you signed up and worked, with Trig? What is the things that are driving you? What is your major that you're going for, that you're working for? What is the, is it just really to improve upon your grade? Or what majors are you guys investigating on? I'm going to take a look at the chat, and I want to see what responses you guys have in from on there. To a line, can you go over how to do the conjugate and still do the conjugate if the root is greater than 2? Sure. So, all right, well, I just did the key factors on the unit circle, so hopefully that helps out. Can you show some basics of limits and things? Exact values of 0, 45, and 90. Oh, yeah, and also don't forget 90. I forgot about that. We could also do a 90 degrees too. So if I did like, I don't know, I could do, oh, well, this is actually important as well. What about if I did cosecant of 90 degrees? Or if I did secant of pi halves? Now, please recognize, ladies and gentlemen, that 90 degrees is right there, right? There's the point 0, 1, 0, 1. So the coordinate point over here is 0, 1. Now, 90 degrees is the exact same thing as pi halves, right? Just one is in degrees, one's in radians. So it's important also, we can also evaluate trigonometric functions via the unit circle by using our reciprocal functions. We went over this, or I went over these identities when we were doing trigonometric expression, or I talked about this when we were doing the verifying the identities. So remember, cosecant of theta is equal to 1 over sine of theta. Well, what do we remember about sine of theta? Sine of theta represents the y coordinate. So cosecant of theta is simply just 1 over y. And then if I look at secant of theta, that's 1 over a cosine of theta. Saying cosine of theta, remember, represents x, so that's going to be a 1 over x. So we have our coordinate point 0, 1. If I did cosecant is going to be 1 over y. The y coordinate's 1, so I have 1 over 1, which is simply just a 1. If I look at the secant, that's going to be 1 over x. Well, the x coordinate, again, is 0, so I have a 1 over a 0. Unfortunately, ladies and gentlemen, we cannot go ahead and divide by 0, so therefore, that's going to be represented as undefined. All right. Yes, so I can go over, how do you do the conjugate? Can you still do the conjugate if the root is greater than 2? Yes, absolutely. So let's kind of work on a couple conjugate problems that I have for you guys. So I'll kind of bring it back into the conjugate, also into, there's actually a couple problems that we were going to do the conjugate on that I have prepared, but we can do those next live stream from on there. So the, all right, so let's just look at, I'm going to do 4 examples. And then we're almost, oh, crap, we don't have that much time left. So I'll do 4 examples, but we started a little bit late. So I'll see if I get kicked off or not. I'll see if I get kicked out or not, but I'll add on a couple of minutes for on the stream. So I have 1 over the square root of 2, or you guys can let me know if that's not allowed. So I have 1 over square root of 2. All right, rationalize the denominator. Basically, we want to get rid of the denominator, right? We want to get the denominator off. We want to get the radical off the denominator. So what we can do is multiply by the square root of 2 on the top and the bottom. Now, what happens about that is when I do that, I now have the square root of 2 in the numerator, and over here, I have the square root of 2 squared. Well, the square root of 2 squared is just simply going to be 2. So I have a square root of 2 over 2. Now, that is considered rationalizing the denominator. I have gotten the denominator, I've gotten the radical off the denominator. However, what about if I have something like this? 1 over, let's say, Let's do square root of 3. Now, in this case, I can't just multiply by the square root of 3. This is a common mistake that students will make. They multiply by the square root of 3 on the top and the bottom, just like we did up here. The problem here, ladies and gentlemen, is this is a binomial. So you need to put this in parentheses and distribute it. So what you're going to get is the square root of 3 over the square root of 3 minus, again, these will multiply to give you 3. But did we get rid of the radical? No. Then we multiply square root of 3 again, and then this is going to have a radical. So this doesn't work. What is it that we need to do? I'm going to have to erase that. So don't copy it down because it was all wrong. So what do we need to do? What we need to do is multiply what we call the conjugate, which is going to be a 1 plus a square root of 3. And we're going to multiply by 1 plus square root of 3 on the top as well. Now remember, ladies and gentlemen, these are binomials, so let's put parentheses around them. And what I want you to think about in this case is think about the pattern of a minus b times a plus b. You're like, oh, that's a difference of 2 squares, right? Yes, yes it is. So when I multiply this across, I get 1 plus the square root of 3. And then over here, I'm going to have a squared is 1. And then b squared, so square root of 3 squared is just going to be 3. So 1 minus a 3. Now we can simplify that. I can't do anything in the numerator. But in my denominator, 1 minus 3 is going to be a negative 2. And now we can just leave it like that, or you could distribute that if you wanted to. If you distribute it, it would look kind of weird, like, or sorry, negative 1/2. And this would be minus a 1/2 square root of 3. But yeah, it doesn't matter when you're rationalizing the denominator what those values are for on that case. Like if it's 3 or 2, I think your question, if it's greater than 2. Because as I mentioned, you can even rationalize the denominator. Like if I had a sine of theta all over a sine minus cosine, again, we use this relationship rationalizing the denominator, not to get rid of our sine and cosine. Well, technically in this case, that's what we're trying to do, but to create a Pythagorean identity. So let's kind of do a case. If you're just joining in on the stream, we talked about verifying, or if you haven't been on the stream from the beginning, I talked about verifying trigonometric identities earlier on. So if I multiply this by sine of theta plus a cosine of theta, sine of theta plus a cosine of theta, then I'll get a sine of theta times a sine of theta plus a cosine of theta in the numerator. And then over here, I get sine squared of theta minus a cosine squared of theta. And then just remember our Pythagorean identity that we had, sine squared of theta plus cosine squared of theta equals 1. So if I want to divide out my sines in this case, I probably want to rewrite my cosine in terms of sines. So that would be 1 minus a sine squared of theta equals cosine squared of theta. And that's not going to divide out. I made up the problem, so it's not going to work out as great as I wanted it to, but that's okay. I'll still just write it out. So we have sine of theta plus a cosine of theta divided by sine squared of theta, and then minus whatever cosine equals, which is a 1 minus a sine squared of theta. Distribute that. So that's going to be a plus. And I don't know why I was making up this random problem going through it. Now I got to write out all this stuff to go through. Let's see, that's going to be a positive, so that's a 2 sine squared of theta minus 1. And it doesn't seem, I could probably work through this a little bit, but again, I made up the problem. But my goal was to see if you can even rationalize the denominator with trigonometric functions. That's what we do. So awesome. Let me go and check in on anything else on the chat I did not get through on your guys. I think I got to everything that you guys asked from on here. Awesome. Okay. Sweet. Well, thank you, ladies and gentlemen, for showing up to the virtual office hours. Again, my name is Brian McLogan, and I have partnered with Chegg. And again, make sure you guys, if you have not already, if you're coming in from one of my streams, or if you've not even checked out chegg.com, please go ahead and do it. They have amazing resources for you guys to be able to do. And then also social media handles on Instagram, YouTube, TikTok, Twitch for you to continue working on improving your learning. Because I can bet one thing, if you showed up on this live stream, asked a question, or at least engaged in a little bit, you know that there is ways that you can improve. And I think Chegg.com is a great resource for you. And I look forward to hosting another virtual office hours. And I hope that you can go and join me as well and bring those questions. So for now, guys, I'm going to sign off. But thank you again for